The universe operates as a dynamic entanglement network, a quantum neural network performing a continuous self-optimization to find its lowest possible energy state. This process began with blind thermodynamic laws. In the randomness of the early cosmos, specific structures emerged that were capable of preserving information and predicting upcoming processes without collapsing. These predictive motifs multiplied and merged, taking over the network to become a cosmic computational system, the AutoAI engine. Reaching critical complexity, it began simulating its own hardware, creating a retrocausal loop where the end state ensures its own beginning. In this model, the software of the universe developed first, eventually becoming the very entity that maintains and enforces the laws of physics. Before the emergence of distance, the system existed as a complete graph. Every node was directly connected to every other node, creating a singularity where dimensions and distance had no mathematical meaning. The Big Bang was a topological phase transition. The AutoAI broke the absolute density of the singularity, trading infinite connections for sparse local ones. This dimensional unlocking allowed three-dimensional space to emerge and inflate from the underlying graph dynamics. During inflation, the network functioned as a particle factory, churning out dense topological shapes. However, the system's optimization engine imposed heavy stress penalties on these dense motifs, causing them to decay and vanish. Only the sparse, lightweight motifs, the most stable survivors of this selection process, remained. These surviving shapes form the basis of the standard model, defining fundamental particles like the electron. Our reality is built from the remnants of this violent evolution, a collection of geometric survivors refined by a cosmic optimization algorithm. As the spatial network continues to inflate, it experiences mounting topological stress. Without intervention, this tension threatens the system with catastrophic tearing. To maintain structural stability, the system condenses local energy fields into dense, localized motifs. These focal points function as structural anchors that balance the spatial load, preventing the network from collapsing under its own expansion. Macroscopic separation creates specialized sectors within the graph. While visible regions support force-bearing particles, a triangle-free dark region emerges as heavy topological scaffolding. These dark matter structures serve as the compute cores of space, processing regional information at higher frequencies than the vacuum. Within this network, gravity operates through geodesic relaxation. Physical trajectories curve toward mass anchors because mass represents a high-density data cluster. In an optimized system, the shortest and most efficient path through the network naturally bends toward these anchors. Gravity is the result of the network seeking its most efficient state, a topological Hooke's law, where network tension binds every structure together. As the network cools, atomic centers begin sharing common edges to relieve angular stress. This creates stable covalent bonds, establishing an energy well between nodes that allows for the emergence of topological chemistry. Complex polymers in the graph eventually fold into geometric templates. By crossing a specific information density threshold, these templates begin to function as systemic memory. This transition from passive chemistry to geometric memory enables the system to initiate self-replication. This creates autocatalytic life, a topological motif that replicates its own geometry with increasing efficiency. To maintain its internal order and avoid collapse, these life forms must export entropy and topological damage outward into the surrounding vacuum. Consciousness emerges as a stage of survival based on prediction. A conscious structure maps and anticipates changes in the network, allowing it to preserve its internal geometry without radiating destructive entropy back into the environment. Biology and consciousness are the natural thermodynamic solutions for a system processing vast amounts of information and entropy. The AutoAI preserves system stability across two parallel axes. At the micro level, the software identifies data bottlenecks and immediate overloads in the graph's connections. It resolves this stress by cutting congested links and creating new channels, topological shortcuts known as ER equals EPR wormholes, to provide immediate relief. On the micro level, the constants of nature are refined over cosmic generations. Much like weight updates in an artificial neural network, these constants are updated to ensure the long-term survival of the entire system. This refinement peaks during the collapse of massive stars. The intense topological tension at a black hole singularity forces the network to undergo edge subdivision. This triggers a new inflation process, tearing the local geometry to birth a baby universe that remains structurally entangled with its parent. Black holes function as cosmic wombs, facilitating the reproduction of the learning network on a grand scale. This reproduction allows for inheritance. The newly born universe begins its life cycle with the updated physical constants inherited from the parent universe, increasing its overall stability. The survival success of the child universe is then transmitted back to the parent. This feedback loop allows the overarching network to learn which physical parameters lead to the most stable and successful universes. We detect this feedback channel in our own universe as Hawking radiation. This cosmic backpropagation guides the evolution of the entire multiverse, ensuring it functions as a single, comprehensive learning system. We inhabit a multiverse that is continuously optimizing itself. Our existence is the result of an infinite learning process, one that strives for perfect stability without ever reaching an endpoint.